Alright guys, so today's just going to be a real quick video. We're going to go over calculating vector components. So let me just go ahead and write this up here. Vector components. There we go. So it's actually going to be a very quick and easy video today. So say we are given the vector f, and these little absolute value signs are going to denote our magnitude and then our vector notation. So this vector f, as let's draw it here, is broken up into x and y components. So a little subscript x and y here. So here's the y component of f, fy, and here's our x component of f. This is fx. So this is f. And so let me erase our title up here. I'm going to assign a magnitude to f so that we can calculate our components. So let's say that f magnitude equals 2. There we go. So, alright, we can change this down here. Oh, actually, I guess we should leave the f here. This is just, actually, I'll take a double take on the complete mathematical notation over here, and we'll just stick with the vector physics. So here we have vector f, and this x and y components, as you can imagine, if these are axes, this is your y-axis and this is your f-axis. So this magnitude of f of fx is basically how many units to the x direction this vector is, and then how many units in the y direction this vector is. So once you understand that, let me blow this equation up a little bit. So here we go. Again, here's our x and y components. Here's our vector. fx, fy, f. All right. So we know the magnitude is 2, and say that this angle bisects at a perfect degree of 45 above the x-axis. So this would also be 45 degrees. So both of these angles are 45. So as we can see here, the angles are not going to be too difficult to calculate. So a simple way to imagine this is using triangles. So we can draw this triangle here. So this triangle would actually be a little shorter. Let me make this a little more accurate. Be about here. So let me draw this line from this point to this point. See, that's where our magnitude begins and ends. So we draw this straight line, sort of straight line. Here we go. To make a triangle. So from here, we can use our tritometric identities, or SOHCAHTOA is a commonly used term to find the magnitude of this vector. So what we would do is we would use this angle that's in relation to the x-axis, and you would plug in a value based on what you know. So what we know here is 2. We know the magnitude is 2. So this is 2. And so we plug in a value to find this 2. So we want to know this x component here. Then we take our calculators. And we use this angle. And we would use, in this case, since this is our hypotenuse, this would be, according to this angle, this x-axis would be the adjacent side. So tangent of theta is equal to our adjacent side, which we will call fx, magnitude of fx. And then, so that's adjacent over hypotenuse is 2. So we can change theta here to 45 degrees. And then we would just plug this into our calculators. So, well, you can switch the 2 over. So 2 times tangent 45 equals the magnitude of your x component, your vector in the x direction. So I'm just going to pull out my calculator here and plug this in. Let's see. Tangent of 45 is 1. So times 2. So our x component, so our magnitude of f of x is equal to 2. And since it's in the directly in the x direction here, you could say that it is this vector is 2. If we label this axis I and the y-axis j, then it would be 2I. Alright, and then we would do the same thing for our y component. So we would just draw the triangle line the top of our vector up here. Again, let's pretend that our magnitude ends here and that I drew the vectors correctly the first time. Change it though. And then we would just do the same thing. So we have our hypotenuse is 2. And we need to find the adjacent side, which is going to be our tangent function. And it would result to the same equation. Would be tangent of 45 I'm not going to actually write it all over again, but it would be 2 times tangent of 45, but instead of f of x, it would actually be f of y. So in this case, we got it pretty simply. We only had to use one function of tangent. In general, if you are dealing with so to complete this, if we wanted to express our vector f in terms of its components, it would be 2i. I hat is our notation for a vector in the I direction. And then 2j hat is 2 in our y direction, and that is our y component. So this is your answer. Now that's using the tangent operation to find your components, which often requires that you draw out the vector on a on an axis and then use trigonometry to determine that you need to use a tangent. A more mathematical approach is just to know that for vector x, for vector f of x, or vector in the x component of f is going to be equal to the magnitude of f times cosine theta, where theta is equal to the degrees above x-axis So if here's your vector, this is your x component, here's your y component, this is theta. If your vector is like this, here's your y component, or your y-axis, here's your x-axis. Now theta is here. And then also, depending on how you solve this problem, you could use theta against the y-axis if you read the y-axis before the x-axis. But in general, we'll get back to the general terms. I'm running out of time here. Our x component is the magnitude of f times cosine of theta, and our y component is going to be the magnitude of f, vector f, here we go, is going to be magnitude of f sine of theta. So this is the general format for finding your x and y components. Here's y, here's x, and this is for a single vector. Alright, hopefully in my next video we can get to finding, calculating quickly these terms of, or these components, and then adding multiple vectors together. So I want to be able to have this vector, and this vector, and this vector expressed in terms of x and y components, and then added together. So we'll probably, just as a sneak peek, start off this one geometrically, and then solve for the components using trigonometry. And then we will also practice a problem where we are given the magnitude of all of these vectors, and then we solve for the x and y components, and then we can just add mathematically. So that is gonna be it for today, and hopefully you'll be there to see how we can solve some vector addition problems using some old math, some new math, and a whole bunch of awesome physics. So hope you guys have a good and awesome day. See ya.